Hi everyone, it's Rohan this side from Spartificial, and in this video I'll help you understand about our upcoming live training and internship program called as Machine Learning for Astronomy. So in total it's a 20 weeks of program that's going to start from 30th of November, in which the first 10 weeks you will spend time in the live training program where you will have sessions with your instructors. I'll be your primary instructor over there. So with me on Saturdays and Sundays for 10 weeks, we'll be having live sessions where I'll be training you about how you can solve different types of machine learning projects in the field of astronomy. And then the remaining 10 weeks of time you'll be spending in our guided internship. And upon the completion of guided internship, you also get chance to secure an LOR from your mentors for that project. Okay. So the main idea that I'm going to talk about in this video is what are the kind of projects that you get to create if you enroll in this live training program and internship batch. So yes, let's get started. In the first project, you will get to create a star size predictor where you're going to first generate synthetic data set that is completely on the basis of linear regression assumptions. So to understand the assumptions of the linear regression, you're going to create this data set following those assumptions, and then using gradient descent optimizer, you're going to train the linear regression to get the line of the best fit, where if you give any kind of star brightness values, it is capable enough to predict the size of that star, and hence the name star size predictor. And the tools that are being used over here is NumPy to generate the dataset, Pandas to handle the data frames, Matplotlib for the visualization purpose of how the true outputs of the sizes are as compared to the predicted sizes based on the brightness values, Fast API to generate the API for the backend, Streamlit for the front end part, Render to deploy our API. Alright, so these are the kind of things that we are going to use in our first project, and let me show you how the output is going to look like. So that's how the deployed application looks like. And the unique thing about this application is that every time you refresh it, it's going to change the background. Okay, you will see that this time the background is different, right? And if I just refresh it one more time, you can see it will have some different background, right? And the main idea of how to use this application is you simply enter the number of stars to generate that data set. Every time it will be a different data set, but based on that it is going to tell you what is the true values of the size of the star based on the brightness plus the predicted values of the stars based on the linear regression model. So by default it gives you 500, but let me change it to 600. I'll click on create dataset and generate the predictions. It is getting it done for us. So this is the generated dataset by our model, and in total it will have 600 values as you can see. And then here is the predicted dataset in which along with the brightness and the true size you are having the respective predictions. Just see how close the true size is with the prediction, right? 12.4 is the true value of the size if the brightness value is 1.37 and the predicted size is 12.2. Just look at how close it is. Now if you want to go ahead and look at the plot of how the line of the best fit looks like as compared to the true size, so you can plot the linear regression, and that's how it's going to look like. It is telling you root mean squared error that is going to have. The black line is the predicted line by the linear regression model, and the blue crosses are the actual values of the size. So this is the kind of project that you're going to create as the first project in this training program. And now let's move on to the second project. So now that you are aware about how this type of machine learning algorithm works, it is time to upgrade your learning about different types of algorithm. In your project 1, you focused on a regression problem. In project 2, you will be focusing on classification problem. Over here, it's no more a synthetic data set, but to use a data set that is a collection of different types of stars, that it be a hypergiant, supergiant, red dwarfs, brown dwarfs, main sequence stars, different types of stars basically. You get to predict the type of the star based on its luminosity, temperature, radius, and the absolute magnitude. And you get to do this with the help of a logistic regression that is powered by scikit-learn library in Python that uses stochastic average gradient as an optimizer in the backend. Then pandas is useful again to generate some kind of data frames. Matplotlib is highly useful for analyzing the type of the data set that is given to you, so that you analyze it, you try to understand it, you do some kind of pre-processing on the data set before you train your machine learning algorithm, and then eventually you use the fast API as the backend and the Streamlit as a front end, and deploy it using render. So let's see how this application is going to look like. So I welcome you all to Star Type Predictor. And in this web application, there are basically three different pages. One is for the introduction of this project, how to use this web application, some of the important note to keep in mind, and then how to get started, right? So basically, it can perform two different things. The first thing is called as single prediction mode, and the second thing is called as bulk prediction mode. In the single prediction mode, you give the information about the properties of only a single star and predict what type of star it is. So by default, we have filled up the values of the temperature, luminosity with respect to sun, radius with respect to sun, and the absolute magnitude of the sun. Okay, so by default, the values are for the sun. So if you click on predict, it is going to say that it's a main sequence star. Okay, so it's using the logistic regression in the backend. It's getting all this kind of values as an input, and then it's predicting main sequence star, which we are showcasing over here. Note that in the backend, you are having your fast API. Okay, it's an API whose endpoint is a predict endpoint. If you click on that endpoint, it is going to get you the output by the machine learning model. Now, just like this, over here, I am having the data for the Betelgeuse star. It is called as a supergiant star, and it has the properties of the star, in which you can see that the radius of a star is somewhere around 700 times the radius of the sun. So let me just go ahead and try to fill this kind of values and see if our model is able to predict it as a supergiant or not. Okay, so radius is 700 times the radius of the sun. Then about the luminosity, it's in between 65,000 to 87,000 something. So let's just choose as 70,000. So I'm going to put the luminosity as 70,000 times as that of our sun. And then the temperature is about in between 3600 to 3800. So let us use 3700. And then about the absolute magnitude. If I check the absolute magnitude, it is negative 5.85. And if I keep this negative 5.85 and then click on predict, it says that the predicted star type is a supergiant. So that's how your app is going to work for the single prediction mode. If you change it to the bulk prediction mode, over here, it first asks you to download a sample dataset. If you're not having the dataset already, the dataset must have the temperature column, luminosity column, radius column, and the absolute magnitude column. Okay, if you're not having this kind of dataset by default for you to test, you can download this sample dataset and try it out. So in this case, you click on browse file and upload this star type properties. It's going to take it as an input, in which you are just going to have only the first four columns: temperature, luminosity, radius, and the absolute magnitude. This predicted type is the output that is given by our model, by our logistic regression model, where it tells us that if this is the kind of inputs of the star, then the type it belongs to is brown dwarf. Like this, we are having multiple stars that we can pass in and get bulk prediction done within just few seconds. So yes, that was about our star type predictor. I hope it has given you a great idea of how this kind of web application is going to look like and what are the kind of things that you are going to build in this training program. Now let us move on to our third project, and this is about lunar terrain segmentation. That if you showcase your model an image of a moon, it can segment it into four different categories. The first one is the big rocks, the second one is the medium rocks, and these are the kind of rocks which your rover might be having some kind of difficulties with. So these are the important types of rocks. Now apart from that, it could be having a small rocks or a normal surface of the moon. Even that can also be detected or segmented. And also the sky. Okay, if rover is able to capture the sky, it can also segment what part of the image belongs to sky. So yes, this is the level of the project that we will be solving, a very important use case in the field of computer vision called as semantic segmentation. And you're going to do this by following all these kind of tools. TensorFlow and Keras is used to train our deep learning model. Pandas again over here to deal with some kind of CSV files that we are having in the project. Scikit-learn to handle the evaluation matrix. Scikit-image to deal with the image processing. Segmentation models to train our model with the help of TensorFlow and Keras. We are also going to use segmentation models which can help you do the transfer learning, provide the unit architecture, and then train the model. And then again, we are going to use fast API and the Streamlit to create our whole web application. So yes, let's look into how is it going to look like. So welcome to the lunar terrain segmentation app. Over here, we are going to upload an image of the moon surface, and it should be at least 480 by 480 pixels. So I'm already having some of the images to try over here. And let's say I'll use Google Image 2 over here. It's going to take some time to process and upload it over here. And then that's how it's going to look like. Over here, there is just like, the surface of the moon without any kind of rocks and the sky. Let's see if I click on segment this image, how is it going to look like? So it's saying segmenting, and let's see how the output looks like. So that's how the AI model has done the segmentation. The sky is green in color, and the surface of the moon without any kind of big or medium sized rocks are given in black color, and that is how it's going to look like. Let me just go ahead and try one more image and show how is it going to perform. And over here, let me use real moon Kaggle 1, and let's see how is it going to perform. Okay, so that's how the surface of the moon is going to look like, with some medium sized rocks and the sky and the other part of the surface also. So I'll click on segment this image. It is going to perform the segmentation, and the sky will be in the green. As you can see, the medium rocks, right, the medium sized rocks are given in blue, and all the very tiny rocks and the other surface of the moon is given in the black color. So that is how your model is actually performing, right? So yes, that was about this project. Now let us move on towards our final project in our live training program and show you how is it going to look like. And this final project is a super advanced level of project in the field of computer vision, where you deal with generative AI. So with the help of generative adversarial networks, specifically the persistent GAN with gradient penalty, we'll be having this ability to generate random images of the galaxies every time you refresh the application. And then along with the pix to pix GAN, that is the picture to picture translation GAN, you can colorize these images of the galaxies. And the dataset that we're going to use for this is called as Galaxy Zoo dataset, that is given out by Zooniverse. And the tools we are going to use to complete this web application is the training and the validation part is taken care with the help of PyTorch this time. Scikit image for the image processing, the pre-processing that we do on the images before we pass it to the main model. And then the fast API and the Streamlit to deal with our web application. So yes, now let me show you how the web application is going to look like. So I welcome you all to Galactic AI. You are already aware about the application, what is it about to do. So I'll be skipping this about the app part, and I'll take you to the Galaxy generator. And over here, it generates the AI generated galaxy image, and this type of images are very close to the training dataset that we have used to train this GAN model, because the aim of the GAN model is to generate the new data which is very similar to the distribution of the training dataset. So because in the training dataset we had a similar kind of images, as you can see over here, it is able to generate an image completely of its own, and every time you refresh it, it is going to generate a very similar looking images for the different types of galaxies that we had in the training dataset. Okay, so you can see that this kind of images are also present. If I show it to you over here, you can see that, right, this kind of lines, it's kind of a galaxy that we are seeing, where we are just seeing the side part of the galaxy, and that's how it's going to look like. And then if you click on colorize it, it is going to utilize the Galaxy Zoo dataset. Okay, this dataset is actually what I've used for the testing part, and for the training part I have used Galaxy Zoo 1 dataset. Okay, and in this case what's going to happen is, if you click on any of the images for the Galaxy Zoo 2, it is first going to convert this into a black and white format, and then allow the AI to colorize it. Okay, and we hope it to be very close to how it looks like over here. And to give you an example, let me take this example of a galaxy 10008.jpg. Okay, I'm going to take this image, I'm going to pass it in the Galaxy colorizer, okay, and show you how is it going to perform. So I'm going to drag and drop over here. If you want, you can also download this kind of images and then pass it over here and show how the output looks like. It uploaded the image in the black and white format, and then AI colorized this image. You can see that it's not exactly the same color, the colors are a bit different, but then that's how it's going to look like. This is the colorized image by our AI, and it's the true color of the galaxy that we have captured with the Galaxy Zoo dataset. Like this, I can show you one more dataset. I'll just go back to the images and take one more image from here. Let's say this time we choose this image. Okay, It is, why is it not scrolling down? Anyways, let me try to just take this image and pass it to our web application and see what kind of color it predicts for this. Okay, it first converts this into a black and white color and then passes this to an AI model. Then AI colorizes that image, and that is the color that it has given to this galaxy. Let me show you how this looks like over here. That's the true color, and this is what AI has predicted. Just look at how good it has predicted, right? So yes, that is about our galactic AI application. And guess what, I've also mixed this kind of feature in our main galaxy generator, that if you want to colorize this level of images, you can also do that. If you click on colorize, it is going to allow the AI to colorize even this type of images. So even though it is involving a lot of noise in the background, right, you can see that the galaxies are still being colored. So I just try to mix both of this kind of capabilities and see how the web application is going to look like. And trust me, it is just stunning. And on top of this, you're also handling a local database where you are storing all this kind of images that is generated by AI. Let it be this kind of black and white images that we got from this data set, or let it be any kind of coloring that application is doing. All of this data is getting saved in the backend. I'll show you how is it going to look like. So that's how our repository is going to look like. If you go to the database, it has 3 different folders. One that is for the generated images, it stores all the generated images. Then L channels is the black and white images that it forms. Okay, the black and white images that it forms once you pass any input to it. If it's already black and white, it does not perform anything on top of that. But if it's already colorized image, then it first converts it into a black and white image and then passes it to the model. And then model generates this RGB data, which is a colorful image, as you can see. So yes, that was about this project. So yes guys, these are the level of projects that you will be creating if you enroll in this machine learning for astronomy in the first 10 weeks of this training program. We started with very basic level of project where we used the synthetic data set. Then we went ahead to create a star type predictor, then the lunar terrain segmentation, and finally the galactic AI, which is a chain AI product that we have created. Now after this, you will have 10 weeks of time where you will create an end-to-end project in your guided internship under a mentor. Over here, I'm going to show you one of the projects that is recently built by one of our team at Spartificial. They used a dataset called as LIGO dataset of gravitational waves, where they use the deep learning skills of transfer learning, state-of-the-art models for image classification, which had a huge imbalance in the dataset. So they also handle that imbalance in the dataset. And the aim was to classify different types of glitches that we have in the gravitational waves dataset. And the tools that they had used was TensorFlow, Keras, Matplotlib, Seaborn, Scikit-learn, and HTML. And the name of the teammates who developed this project as a part of their internship is Ashutosh, Abuli, Deeplakshmi, and Khushi. So let me take you on how that application is going to look like. And I'll just take a screen recording of their YouTube video, and I'll also provide the link of their whole project in the description if you think it is useful for you to go ahead and take a look at the complete project.
Follow the link to open the actual app. Now, click on Choose Files, select the images you want to upload, press Upload and Predict. The app will then display the predicted class along with the confidence level for each image. If you want to save the prediction as CSV file, simply click on the Download CSV button and it will do that.
So yes guys, that was the web application created by our team at Spartificial as a part of their internship project, where if they give input of the gravitational waves data, they can classify it as what type of glitch it belongs to. Now you can also build a project like this of your own during your internship project as a part of one of the team at Spartificial. So yes guys, if these things have given you an idea of what are the kind of things we offer in our machine learning for astronomy training program plus the guided internship, and if you're interested to enroll into this, then you will get the link of the direct enrollment in our description. So yes, I'll see you in this program. Bye bye.